Well, welcome to Chapter 10. Chapter 10, we're going to do a deep dive on gases. I know we've been considering gases for a while, but there are some things that are kind of special about gases compared to the other phases of a substance. And we're starting a little differently in that I have a quote from someone here. And the reason why I have this quote is because one of the things that we're going to have to understand something about as we consider gases is pressure, because gases are really affected by the pressure on them. And some of the units that we use for gases you may not be familiar with, but one of them is named after this man here, Blaise Pascal. Blaise Pascal was a famous Christian scientist. He was a mathematician. He was a philosopher. And he loved the Bible, loved to study God's Word. He's famous for some different sayings, but this is not the saying that's quoted in the book. But I love this one. And if you've ever heard a phrase that's something like, "We all have a God-shaped hole in us," that's basically a paraphrase of what Pascal said here. And so this is what Pascal said. He says, "What else does this craving," and what he's talking about is this desire that we have. What else does this craving and this helplessness proclaim? But there was once in man a true happiness, of which all that now remains is the empty print and trace. In other words, we are seeking satisfaction, he says. I actually just heard a message today from the first chapter of Ecclesiastes, and the preacher was talking about that, how Solomon there in Ecclesiastes, he is running after satisfaction. He's trying to find it in all these areas, and he keeps coming back to this phrase of vanity of vanities, all is vanity. And so this craving, this desire for satisfaction, there's just an empty print and a trace left, Pascal said. Well, where did we lose that? We lost that in the garden when man fell in sin, right? And so what does man do to try to fix that? Well, instead of going God's way, right, we go our own way, and we foolishly do what he says in the next sentence. It says, this emptiness, he tries in vain to fill with everything around him, seeking in those things that are not there the help he cannot find in those that are. Though none can help, since this infinite abyss can be filled only with an infinite and immutable object. In other words, by God himself. And so I love that. The idea is we can run after all these things, and that's exactly what Solomon did. He tried to find, satisfaction in power and in wisdom and money and women. And I mean, he had influence and he had great wealth, and he was able to explore all of those paths more than any of us could. And yet he got to the end of it all and he said vanity. And it's because the only thing that can fill that satisfaction, the only place where we can truly be satisfied is in God himself. And so God's way is Jesus Christ, right? I am the way, the truth, and the life. No man comes to the Father but by me. And so satisfaction is found only in him alone. So I thought that was a great way to kind of start off this lesson. Was just thinking about the words of Pascal and reminding ourselves that true satisfaction is only found in Jesus Christ. Well, let's go ahead and dig into some of the things that we need to know as far as the chapter goes in order to do these problems. And like I said, pressure is a big deal when it comes to gases. So let's understand what pressure is. I'm going to give you a formula for pressure, and that formula is that pressure is equal to force over area. All right, so simply put, pressure is a measure of how much force is exerted over a particular area. Okay, and so if we look at the units for that, force we would measure that in newtons, named after Sir Isaac Newton, and area we would measure that. We're used to measuring that in the metric system in meters squared, and so basically a newton over a meter square is exactly what a Pascal is. We abbreviate the Pascal unit with PA, and so that is a newton over meter squared. All right, so that's one unit you need to know as far as pressure goes. Another unit that we will use, actually this is probably the one we will use most frequently, is atmospheres, abbreviated as ATM. This is what we use for atmospheric pressure. And so 1 ATM is kind of the normal air pressure at sea level. And so that one we're going to see a lot in our formula. So that's another one you need to know, need to be aware of that unit. Also, we won't use this one much in this chapter, but I do want you to be aware of it. MMHG. If you look at the periodic table, Hg is the symbol for the chemical symbol for mercury. And so MMHG stands for millimeters of mercury. You might see that on a barometer, may be measured that way. And then also the last unit is the torr unit. Now, interestingly, I talked about using this for a barometer, but torr is named after the inventor of the barometer. And so that's another unit that we'll occasionally use for pressure. Now, something that you also need to memorize, in addition to being familiar with these units, knowing that they're pressure units, I also want you to know that 1 atm, like I said, that's the pressure at sea level, the atmospheric pressure at sea level. 1 atm is equal to 760 torr. So I want you to be able to convert back and forth between atms and torrs. Okay, so let's go a little bit further, and before we before we end this video, I want to mention a couple of laws to you, and one is Boyle's law, and many consider Robert Boyle to be the father of modern chemistry. So this is a well-known name in chemistry. Interestingly enough, like we find so often as we look at history and science, this guy was an outspoken Christian, right? He believed in a mighty creator. And he wrote that his study of nature often led him to exclaim with the psalmist in Psalm 104:24, "How manifold are thy works, O Lord, in wisdom hast thou made them all." And so as he was studying the natural universe, it just caused him to stand in awe of God. And in his final speech to the Royal Society, he urged them to remember to give glory to the one who authored nature. So he was encouraging his fellow scientists to make sure, as you study these things, give glory to the Creator. If you remember from Romans 1, you see like a dark cycle, downward cycle, as men get further and further away from God. And that begins with them beginning to worship the creation rather than the Creator. And so Boyle was urging them not to make that mistake, but give glory to the Creator. Well, Boyle's law says this. Boyle's law says that when we're looking at a gas, the pressure times the volume of a gas in one set of conditions is equal to the pressure times the volume of the gas in a second set of conditions. Or another way to think about this is that PV is a constant. Pressure times volume is a constant when you're dealing with a gas. So again, this is one set of conditions, and this is another set of conditions. For the same gas. All right, and so that's why we say it equals a constant, because if you take the pressure and the volume under one set of conditions, whatever the pressure is and the volume is in one scenario for that gas, if you later down the road the pressure increases, well, the volume is going to adjust itself, so P times V is always equal to the same number. All right, so P1 times V1 equals P2 times V2. And what we see by that is that as P goes up, V is going to go down. All right, so they're inversely proportional to one another. When P goes up, according to Boyle's law, when P goes up, V goes down. All right, because P times V is equal to a constant. Now, another important law is called Charles' law. And Charles's law says that that V1 over T1 equals V2 over T2. And again, we could write this generally that V over T for a gas is equal to a constant. All right? So again, the volume over the temperature under one set of conditions for a gas is equal to the volume over the temperature of the same gas in a different set of conditions. So if the temperature is really low, whatever the volume over the temperature is in that scenario will be the same as if you raise the temperature, what the volume over the temperature will be in that case. And so what we see with Charles's law is that volume and temperature for a gas are directly proportional to one another. So in other words, as one goes up, the other one goes up. And or we could say, we could add it to this here, since volume went down in that one, temperature will also go down, right? Whatever volume is doing, that's what temperature does also. Now, the other thing that we need to make sure that we understand regarding these gas laws is we need to talk about a new temperature scale, all right? And so we're familiar with using Fahrenheit and familiar with using Celsius for our temperature. But whenever you're using these particular equations, we need to always use the Kelvin temperature scale. So I'm not sure if you've heard of that before or not, but it's also called the absolute temperature scale. And the reason why is because there's a picture on page 296 that shows it's a graph of the volume and the temperature of a gas. And as that temperature changes, pressure is being kept constant in that graph there. And you'll notice that for these various gases, when you look at the data, they all kind of converge on a single point. I guess from your perspective, it's going to look like that. They converge down on a single point on that graph. So let me just to kind of show what the graph looks like here. It's doing something like this. So I'm going to draw a dotted line here and then a solid line. So when we plot the volume and the temperature on a graph, and let's see, this is page 296. I'm sorry, I didn't have that. I wasn't open to that page. So let me see what's our x axis and what's our y axis. So it looks like temperature's on the bottom, right? Temperature's over here and volume's right here. And so what this tells us is that if you plot the volume and the temperature for various gases, notice they all converge on this point down here. Now the reason we have a dotted line is because the temperature never actually gets that low for any of these gases. But as we extrapolate that data, in other words, we took it on down assuming that the temperature could go all the way down to zero, they would all converge on this one point. And so this temperature that can never naturally be reached, this 0 Kelvin, is what the Kelvin temperature scale is based on. And so the reason we use Kelvin for these gas equations that we have here is notice where temperature is in our gas equations. Temperature is on the bottom of these fractions right here. Well, if we have T on the bottom of the fraction, what has to be true about the denominator in that fraction? It can never be what? It can never be 0, right? And so by using since we never reach 0 Kelvin, by using the Kelvin temperature scale, we're assured that we'll never have division by 0 in these gas laws. Now, Kelvin is a pretty simple thing to calculate if you have what the temperature is in Celsius. And so Kelvin, which is just represented by a capital K, is equal to degrees C plus 273.15. So not hard at all, just simple addition there to go from Celsius to Kelvin, right? Pretty easy conversion to make, but you need to know this conversion equation here. You need to be able to convert from Celsius to Kelvin. And there's a simple problem on page 296, a simple example where they basically give you a temperature in Fahrenheit, and so you have to first convert that Fahrenheit temperature to Celsius, and then you can figure out what that Fahrenheit temperature would be in Kelvin. You've always got to convert to Celsius before you change it to Kelvin, because our Kelvin equation only has Celsius in it. Okay? Now, all of that being said, when we talk about Boyle's law and Charles's law, you don't have to memorize those, all right? And the reason why is because we combine those laws together into what we call the combined gas law. And so this is the one that you need to know, all right? The only one that you'll have to have memorized in order to do the problems in this chapter is the combined gas law. And the combined gas law says that P1 times V1 over T1 is equal to P2 over V2, P2 times V2 over T2, right? So the pressure times the volume over the temperature for a gas in one set of conditions is equal to the pressure times the volume over the temperature for a gas in a second set of conditions. And so if one of these values is constant, right? So for example, let's say you had a problem and it said that the pressure was constant throughout, but then the volume and the temperature changes. Well, if pressure was constant, then you would just remove the pressure here, and look what you have. You have Charles's law. If they said the temperature was constant for this particular problem, then you would remove the temperatures, and look what you have. You have Boyle's law. So you can get the other two laws just from this combined gas law. So we're just going to use this one, and this is the one you need to memorize. But now remember, you must always use Kelvin for this. Must always. This is super important. Must always use Kelvin for temp. All right. So just to do a quick example of that, on page 298, a gas expands under constant pressure. If it has a volume of 2.12 liters at 25 degrees Celsius, what is the temperature in degrees Celsius when it reaches a volume of 5.09 liters? Well, again, we're given Celsius here, and we just said we have to convert it to K first. So the Celsius that they gave us was 25 degrees Celsius. What is that in Kelvin? Well, in Kelvin, that's going to be 25 degrees plus 273.15. And so maintaining the correct number of significant figures, we would get 298.2 as our Kelvin temperature. And it was a constant pressure in this, so we can ignore the pressure for this particular one. So we're just doing V1 over T1 equals V2 over T2, right? They gave us two volumes, 2.12 liters at 25 degrees Celsius, so 2.12 liters, and we converted 25 degrees Celsius to 298.2 Kelvin. That's supposed to be an L for liters, is equal to the second volume, which was 5.09 liters, over the second temperature. And all we have to do is solve for temperature here, right? We would just say T2 is equal to, just doing the algebra with this, we get that T2 is equal to 298.2 K times 5.09 liters divided by 2.12 liters. And so when we do the math for that, looks like we're going to get 716 K. All right. Now this problem says, what is the temperature in Celsius? So now we've got to do the reverse to figure out the Celsius. If C plus 273.15 is what K is equal to, then if they give us K, we're going to have to subtract 273.15 to figure out the temperature in Celsius. So we get 716 minus 273.15 to give us a final value of 443 degrees Celsius, right? So that's how you can use the combined gas law to figure out a missing value under a certain set of conditions. Now the way it's going to be easy to tell when you use the combined gas law, because they're always going to give us two sets of conditions, right? If the problem is constructed in such a way where you're given two volumes or two temperatures or two pressures, then immediately you're thinking, I'm using the combined gas law for that. So it should be really easy to pick out when you need that. The key though is, don't forget, you always have to use Kelvin when you're using these gas law equations. All right, I'll see you in the next video.